Okay, in this video I'm going to cover probability. So we will go over basic concept of probability. We will cover multiplication rules. We will cover addition rules and additional topics in probability and counting. So basic concepts of probability. We will learn what means sample space, simple events. No, we don't need it because we are not going to use it. Fundamental counting principle, that's what we're going to cover. I'm going to skip this. Classical probability, empirical probability. Determine probability of the complement event, that's what we will cover. And instead of tree diagram, we will use only fundamental counting and principle, fundamental counting, and how to find probabilities. So let me make it crystal clear. We are going to cover this one. We are going to cover this. We are going to cover this. And we are going to cover this piece. Okay. All right. Probability experiment. Well, it says clearly action, trial, through which specific the results are being obtained. But result can be results can be count, it can be measures, it can be response. Okay? Outcome. Any the outcome, any result of single trial we call outcome for the probability experiment. Those are basic stuff. I just want you to get familiar with definition. That's all. Sample space. Sample space, all possible outcomes we call sample space. Event, if you have more than one event, outcomes, let's say outcome can be more than one choices, so then we have event. So those are basic understanding. Okay, let's talk here. Examples. Probability experiment, rolling a die. So outcome, if you roll a die and it faces with 3 up, then outcome will be 3. Sample space, all possible outcomes, because die has a 1, 2, 3, 4, 5, 6 sides. That means the full sample space, all possible outcomes are going to be 1, 2, 3, 4, 5, 6. Yes? Event, remember we said event is more than one outcome. So when we say what's the probability, what outcome can be if die is will land with even number up. That is going to be 2, 4, and 6, right? Okay. So let's identify sample space here. We are dealing with probability experiment that consists of tossing a coin and then rolling a die, 6-sided die. So what will be sample space? When you toss a coin, your sample space, you will have 2 outcomes, right? There's a sample space. It's going to be either head or tail, correct? Head or tail. But when after that, when you roll a die, with head you can have 6 outcomes, right? Head, and 6 outcomes, head 1 through 6. Or second outcome will be tail and then tail 1 through 6, right? Okay. And total will be 12. So how to know total amount of outcomes or sample space without breaking down into tree diagram? 2 outcome, very easy. 2 outcome is a sample space of tossing a coin is 2. Sample space of rolling a die is 6. 2 times 6 is 12. And that's what we have, 12. Very simple. Okay. I'm skipping all these simple event things. We're not going to use it, so I don't want to pack your head with something we're not going to use it. So here is a question. You roll a die. Event B is rolling at least a 4. This is gonna be not simple event, right? Because at least 4, because you can have 4, 5, 6, more than one outcomes, correct? Okay. So finally we are getting to fundamental counting principle. Fundamental counting principle, it says if one event occur in m ways, second event occur in n ways, and the total number of ways that include every single case, it's gonna be m times n. So let's do it based on examples so we can understand. Here is example. You want to purchase the car. And here are 3 possible manufacturers: Ford, GM, Honda. Car size, 2 car size, compact, mid-size. And color is white, red, black, and green. So how many different ways can you select one manufacturer, one car size, and one color? Use a tree diagram to check your result. Well, we don't need to use a tree diagram to check a result. We will page it slightly. But we have 3 manufacturers. We have car of 2 size, and we have 4 colors. So it's going to be 24 choices, right? We're going to choose 24 choices. Yes? Okay. Here is 24. Ford, GM, Honda. Every case has compact and mid-size. Compact, mid-size. Okay, and you have all these colors for compact: white, red, blue, green, white, red, blue, green, and so on. Total will be 24. Okay, those is counting principles. So when every single element is participating in the calculation, and you want to know total how many possible choices you have, you take all choices, multiply by each other. Skipping classical, theoretical, this stuff, we're skipping all this. So, well, I can use this as a probability example. Okay, let's do this one because it can be helpful as a probability case. Okay, so let's see. You roll 6-sided die. Find the probability of each event. What's the probability that you will roll the die and it will land with 3? So how many elements we have, how many sides on the die you have with 3? Only 1, correct? Out of how many total? 6, yes? So it's going to be probability 1 over 6. Probability of 3 is going to be equal 1 over 6. One thing you need to understand in the case of probability, that the value is not important. It's important how many times that case happened. So, because if I ask what's the probability of rolling a 4, it's still going to be 1 over 6. Probability of rolling 5, it's still going to be 1 over 6, because it's not about 3 or 4 or 5, it's about how many of 3s, how many of 4s, how many of 5s, and each one of them is on the die only 1. So therefore each one of them will be have probability 1 over 6. Rolling a 7, what will be probability rolling a 7? 0. Why? Because there is no 7 on the die. Tricky question, isn't it? What's the probability rolling a number that less than 5? So less than 5, how many numbers we have? 1, 2, 3, 4. Yes? So how many elements, how many choices? 4? Out of how many? 6. So probability for rolling less than 5, it's going to be 4 out of 6, or 2/3. Okay? That is going to be 2/3 is 0.67, which is 67%. I hope we are doing good. The entire sample space, what is it going to be? Every single outcome, right? From 1 to 6. That will be our entire sample space. Okay? So here we already covered 1 over 6. If you divide, will be 0.167, which in the format of percentage will be how much? 16.7%. Probability of rolling a 7 is going to be 0. Probability, it's a percentage, yes? Nothing else but percentage. Is 0% because there is no 7. And probability of less than 5, it's going to be 1, 2, 3, 4. 4 of them out of 6, which will give you 0.667, approximately 66.7%. Okay. Not going to empirical. Not going to this one anymore. Skip this one, because we are not going to use in the score, so I don't find it necessary to cover this if we are not going to do it. Okay, let's do this one. This one is also probability that we are going to explore, it's related. So classify the statement. Okay, the probability of winning 1,000 ticket raffle with 1 ticket. So 1 out of 1,000, right? The probability of winning 1 ticket that is a winner among 1,000. So it's going to be 1 out of 1,000. That's all it is. Simple as it can be. Range of probabilities rule. This is important. So it can be between 0 and 1. Between or probability of event greater equal 0%, less equal 100%. 1 is a portion wise of 100. 0 portion wise of 0%. Okay? Probability or percentage can be maximum 100 and minimum 0. When you have 50%, 0.5, that means it's even chance not to happen versus to happen of that event, right? Okay. Complement. What is complement of event? If I say there is a 60% chance that it's gonna rain, complement will be, that means 40% chance it's not gonna rain, right? If I say there is 30% chance it's sun is gonna shine, that means 70% chance sun is not gonna shine. So it's a complement. But the bottom line is, if I add this 30%, add with 70%, I'm getting 100%. Which means, if I know one of them, let's say E is the probability of our event, plus probability of complement of the event, we call prime, is equal 1, portion-wise, which means, if I know probability of event is 40%, or 0.4, then probability of complement, it's going to be 1 minus 0.4, right? Which will be 0.6. Yes? It's very straightforward. All right, let's solve example here. Probability of the complement of an event. So you have survey a sample of 1,000 employees at the company at record age of each. Find the probability of randomly choosing an employee who is not between 25 and 34. Who is not between 25 and 34. Two ways to solve this problem. One way is, so find the age probability for age 25 and 34. So it's total 366 people for the age 25 and 34. Among how many people? Among total 1,000 people. So here it is probability of 25 to 34. It's 366 over 1,000. But we are interested the age that are not between. So this is probability for 25, 34. The ones that it's not, it's going to be 1 minus 0.366, right? Here it is, 1 minus 366 over 1,000. And the answer will be 0.634. Why do we deduct from 1? Because we said complement, probability of complement of event and plus probability of event is equal 1. So if probability of event is equal 366 over 1,000 or 0.366, then probability of the complement is going to be 1 minus 0.366, which will be 0.634, which is equal 63.4%. Okay? We're not going through this one. Let's do this problem. The college identification number consists of 8 digits. Each digit can be between 0 all the way to 9 digits. Find the probability of getting your college identification number when randomly generating 8 digits. Okay, we totally generate, 8 digits. So it's gonna be, let's do this way. from 1 to 8 digits. Each number can be between 0 and 9, which means 10, right? Total. So that's mean number 2 also can be total 10 versions, right? 10 digits. Number 3, one of the 10 digits again. Number 4, one of the 10 digits. And so forth. So 10 multiplied by itself, how many times? 8 times, correct. Or it's going to be equal 10 to power 8. Yes? Let's see. Here we go. Multiply 8 times, or 10 to power 8. Which will be 100 million possible identification numbers. And the probability for your ID is going to be 1 out of these 100 millions. Because you get one ID only, right? So you can see. Okay. So this is 3.1, we covered that. Now we're getting deeply into probability. So which will be next section, 3.2.